Today, we're getting into something pretty central for a lot of you homeschooling parents, especially if you're using classical conversations.
We're zooming in on mathematical proofs,
We want to unpack the basics of proofs from the math map.
make it feel a bit more approachable.
Think of this as a friendly pregame chat before you dive in with your seventh grader.
And we're leaning on some great work here. Some fellow homeschool parents over at Scholars and Socials put together a briefing doc and study guide. Super helpful stuff. So let's start right at the beginning. What is a mathematical proof? It sounds intense.
It does, but at its core, it's really just a logical argument, an explanation.
Yeah, showing why something in math is true. Not just that it is true, but the reason behind it using logic.
Step-by-step reasoning.
Establishing it without a doubt based on the rules of math.
And the Scholars and Socials guide, it really highlights this. Once something's mathematically proven, it's solid, always valid.
Within that system, yes. It provides certainty. It's not everyday opinions where things might change. A good proof is built on logic.
Which, as the guide points out, is different from just, say, trusting something you read online without checking.
Totally different. Proof requires rigor.
Okay, rigor. So part of that rigor involves understanding some key terms, right? The guide lists a few. Let's start with axiom.
Axiom. Okay, think of it like the absolute basic rules of the game. Stuff we just agree on from the start.
Except it is true, no proof needed for the axiom itself. It's a starting point.
Exactly. Like in geometry, a straight line can be drawn between any 2 points. We just accept that.
Got it. Okay, next term. Proposition.
A proposition is basically just a statement. Could be true, could be false. It's like making a claim.
So it's something you might need to prove or disprove.
Precisely. Which leads us nicely to theorem.
That's when a proposition has been proven true, right?
Yes. Using those logical steps, building on axioms or other theorems, it's a major result, a proven fact.
Okay, theorem. Proven fact. Now what about a lemma?
A lemma is like a mini theorem. It's a smaller result that you prove first because it helps you prove a bigger theorem later.
It's a stepping stone.
Perfect analogy. A helpful stepping stone on the way to the main result.
Cool. And then corollary.
Corollary, that's an immediate consequence of a theorem. Once you've proved the theorem, the corollary just follows easily from it.
Like a little bonus fact that drops out.
Yeah, a direct result.
Okay. And one more thing, sometimes seen at the end. QED.
Yes, QED. It's Latin, stands for quod erat demonstrandum.
Which means?
That which was to be demonstrated. It's like the little flourish at the end saying, ta-da, we did it. We proved what we set out to prove.
Nice. Okay, so we have the words. Now, the Scholars and Socials guide mentions different ways to actually show a proof, different styles.
Right, different formats. One common one, especially in geometry, is the 2-column proof.
Okay, 2-column. How does that work?
It's very structured. You literally have 2 columns. On the left, you write your statements, each step of your logical argument.
And on the right?
Your reasons, why each statement is true. You might cite an axiom, a definition, maybe a theorem you already proved. It's very neat, very organized.
Keeps things lined up. I can see how that would be helpful for learners.
Definitely. Then there's the paragraph proof.
Less formal, I'm guessing.
Yeah, exactly. You basically just write out your logical argument in sentences, like you're explaining it conversationally. But it still has to be logical, step by step.
So more like telling the story of the proof.
That's a great way to put it, telling the logical story.
Okay. Then there's one called proof by contradiction. Sounds a bit counterintuitive.
It's a clever one. You start by assuming the opposite of what you actually want to prove is true.
Why would you do that?
Because you then show that this assumption leads to something impossible, a contradiction, something that breaks the rules of math.
So if the opposite leads to nonsense, then the original thing must have been true all along.
Exactly. It's like a detective eliminating possibilities until only the truth remains.
Clever.
Yeah.
The guide also mentions proof by induction, but maybe briefly.
Yeah, induction is usually for proving things about sequences or patterns that go on forever. Does this pattern hold for all numbers?
How does it work, roughly?
You show it's true for the first case, like the first domino. Then you show that if it's true for any one domino, it must be true for the next domino.
So if the first falls and each one knocks over the next,
then they all must fall. It's powerful, but maybe not the main focus for most 7th graders right away in math map. Good to know it exists, though.
Definitely. And the last one mentioned is proof by construction.
This one's quite direct. You prove something exists or is true by actually showing how to make it, how to construct it.
Like proving you can draw an equilateral triangle by actually giving the steps with a compass and straight edge.
Precisely. You build it, therefore it can be done.
Okay, so we have these different methods, but let's back up a bit. Why bother? Why are proofs so important? Why put 7th graders through this?
Great question. Inside math itself, proofs give us that certainty, that solid ground. You understand why things work, not just that they work.
It makes the math make more sense, deeper understanding.
Absolutely. It builds a foundation for tougher stuff later. You can't build high without a solid base.
And the guide really stresses benefits outside of math too, right?
Oh, hugely. This is maybe the most important part for many kids. Learning to do proofs builds incredible logical thinking skills.
How?
You have to break down a problem, think step by step, justify every single move, spot flaws in reasoning.
Skills you need everywhere, like writing an essay, making a decision, even just figuring out if an advertisement makes sense.
Exactly. It's training the brain to be organized, critical, and logical. That's invaluable.
Okay, that's a really strong argument for it. Now, the Scholars and Social stuff mentions geometry examples are common in 7th grade math maps.
Yes, geometry is a natural place for proofs early on. Think about proving triangles are congruent, same size and shape.
Right, using this as side. If all 3 sides match, the triangles match.
Yeah, or SAS side angle side.
Yeah.
Or SA angle side angle. Proofs show why those shortcuts actually guarantee congruence. They aren't just random rules someone made up.
They follow logically from basic geometry axioms.
Correct. Same with parallel lines. You know, when another line cuts across them, a transversal.
Yeah.
Proofs show why certain angles created there have to be equal, like alternate interior angles or corresponding angles. It all connects back logically.
Okay, so let's talk about those connections. Axioms and theorems in action. Can you give a super simple axiom example a 7th grader might see?
Sure. Remember we mentioned axioms are starting points? A common one is about corresponding angles.
Okay.
It says, if you have 2 parallel lines and a transversal cuts across them, then the angles in the same corner at each intersection are equal. They're congruent.
Like top left angle at one intersection matches the top left angle at the other.
Exactly. We accept that as a fundamental truth of parallel lines in Euclidean geometry. That's an axiom.
And how does a theorem build on that?
Using that corresponding angles axiom, plus maybe some other definitions or axioms, you could then prove a theorem. For instance, you could prove that alternate interior angles must also be congruent.
So the theorem is a result you demonstrate using the axiom as a tool or a starting point.
Precisely. You build upon the accepted truths. Axioms are the foundation. Theorems are the structure you build logically on top.
That makes sense. It's like building with Legos. You need the basic bricks first.
Good analogy.
The guide also had a little FAQ section, which is helpful. It revisits the definition of proof logical argument. We covered that. And it stresses again why axioms, postulates, which are similar to axioms, and definitions are crucial starting points.
Yeah, you can't prove anything if you don't agree on the basic rules and what the words mean.
Yeah.
Need that shared foundation.
Makes sense. Otherwise, you're just talking past each other.
Totally.
It also asks again about the difference between proposition, theorem, and corollary. Quick recap.
Sure. Proposition. A statement waiting to be proven, maybe true, maybe false. Theorem. A proposition that has been proven true. Corollary. An easy consequence that follows directly from a theorem.
Got it. Proposition, proof, theorem, corollary. Kind of a chain.
In a way, yeah. And the glue holding it all together? Logical reasoning. Every single time. That's the engine of proof. If the logic fails, the whole thing falls apart.
Okay, so let's bring it back to the parents listening. They're looking at the math map, maybe feeling a bit nervous about teaching proofs. What's the main takeaway here?
I think it's don't be intimidated by the formality. Remember, at heart, it's about why. Why is this true? And the answer is always logic.
So focus on that logical flow. Help your child see the step-by-step connections.
Use diagrams, especially in geometry. Make it visual. Talk through the reasoning. Don't just focus on memorizing the steps of one specific proof. Focus on understanding how proofs work in general.
It's more about developing that logical muscle than just getting the answer right on one problem. This might look challenging, but it's actually a really valuable journey.
It can actually be quite satisfying for both you and your student when you see how the logical pieces click together.
A journey of discovery. I like that.